Okay, so let's start the afternoon session. The first speaker is Masahito Yamazaki from the University of Tokyo, and he's going to tell us about Vertex operator algebras as hierarchization of the Quiver variety.
Okay, I think the microphone is on, so I hope it's not too much of a volume. So, first of all, let me thank the organizers for, first of all, organizing this event. It's always great that University of Tokyo and Kias, and so there is a interaction between Japanese and Korean communities right here. I myself have been benefiting a lot from that collaboration. In fact, I've been to this building for many, many times, actually more than 10 times, I'm sure. I even organized a workshop here. But probably this is my first time to come here to officially visit the math department. Usually I visit the physics department. And in that spirit, today I'm going to talk about some topic in mathematical physics. So this is in collaboration with Yono Koman, Myunbo Sim, Yehao. All of them are or were at IPMU as a postdoc. In fact, Myunbo Sim, that's a clearly Korean name. He was actually a graduate of Kyunghee University right over there. But in any case, and then so the paper, one of the papers appeared last year in HepTH. That's already out, and which contains some mathematical statements too. But some of the proofs we didn't provide, so we're trying to write it up in a separate math paper. Okay, so and then that's the content I'm going to explain. But I suppose that I would assume that this is a very broad audience, some of whom are experts on some of the things I'm going to say, but not everybody. So let me try to provide a context to make sure that at least people know what I'm talking about. And interestingly, I was attending the this morning session and I realized that some of the both talks in a sense has something to do with what I'm going to say, although maybe not too explicit, but so if you get bored, you can think about, okay, what is this crazy guy doing? And then try to connect it to other talks, which can be fun. So, okay, so what is the topic? Well, broadly speaking, before coming to anything specific, one of the fascinating aspects of the relation between physics and mathematics is, of course, it's a mutual interaction. So, development of physics motivates the development of math and physics, etc., etc. So that's a fascinating story. But from mathematicians' perspective, this is not the end of it, because physics might be sometimes like a black box. But the good thing about the physics is that it sometimes connects to different maths. For example, if you're a mathematician, you might say, let's say a geometer, for example, and then you belong to the geometry subsection of your math department, and then you might feel like algebraists, like they're far away, like they might look like different people. But sometimes you realize that some geometry problems come from physics. And what's interesting about physics, physicists per se, they don't care about whether something to do with the geometry or algebra. It's just physics. And if you do quantum field theory, there are all sorts of things, algebraic aspects, geometric aspects. So you are inevitably led to some different mathematics, which means that it might sometimes serve as a portal to different mathematics. It's like a wormhole. So it's a black box, but it's actually sometimes it's a good black box, so that you can try to connect apparently different branches of mathematics. So even if you're a pure mathematics viewpoint, the physics provides such a good unifying perspective on various different mathematics. And in fact, that's partly reflected in the title of my talk. So I'm going to talk about the vertex operator algebras. As the name suggests, it's an algebra, infinite dimensional algebra. You can talk about the representation theory, but it's an algebra a priori. And then the other thing is the Quiver varieties. Well, varieties, so it's algebraic, sorry, but it's kind of geometric, yes. So the geometry and then so these are, at least traditionally, these are completely different topics as far as I know. But it turns out that you can connect them in a very precise way, and which is motivated by physics. But in the end, there are some precise mathematical questions and the mathematical research topics you can construct, and that's what I'm going to talk about. Okay, so what is the starting data? Well, the starting data is going to be the Quiver. So let's see what is the Quiver. So, well, let me write down an example of the Quiver. let me write it relatively large because I'm going to add more and more information in this picture. So let's say there is a graph like this, and then there are lines connecting them. So this is an example of the quiver, and for each vertex, so this is a vertex, I'm going to add the so-called framing vertex, which is connected to that. So I'm going to draw a frame vertex, and then for each vertex, you're going to add the numbers, non-negative integers, such that this represents a vector space. So there is going to be some vector space, B1, B2, B3, whose dimension is small bi. And then similarly, you have W1, W2, W3. You have some vector spaces, W1, W2, W3. So this is an example of a starting combinatorial data. So this is a quiver. That's what I mean by quiver. So the starting data is the quiver. Starting data is a quiver, which is a set of vertices. So this is a vertex. And the arrows I denote by Q1. I'm not going to use this notation too much, but the Q is a quiver. Together with dimension vectors, B and W. So set of B's and W's, like the one I wrote above. So this is the defining data, combinatorial data. Now, starting from this data, there are many different things you can associate with it. But if you're a physicist, you're going to associate the theory, three-dimensional, n equal 4, supersymmetric, Quiver gauge theory. And of course, since this is defined from this data, there should be some corresponding objects corresponding to Q0, Q1, etc. And in the physics jargon, Q0 specifies the gauge group. It's called an n equal 4 vector multiplet in supersymmetric jargon. But then Q1 is the flavor. So in particular, there is a gauge group, Cu, U, B. So this is the product of U and Bi at each vertex. So there is a unitary group. You might imagine that there is a unitary group for each of the vertex, and this is the total group. So this is the definition of the theory. So now this theory itself, you can define even perturbatively. If it's a perturbative theory, as a perturbative theory, you can make sense of it completely rigorously mathematically. But that's not the main point. But my main point is that this is a physical theory, and you want to extract some mathematics out of this. So what's going to be that mathematical structure? Of course, one is the vertex operator algebra, and another is the Quiver variety. Yes?
Q1 arrow corresponds to one flavor.
Yes, that's right. So arrow corresponds to flavor. Yes. Yeah. So or maybe I shouldn't say. Maybe matter is a better word actually. Matter. So it's like a quarks, for example. Yes. So so this is a gauge group. If it's a QCD, for example, group, and this is a matter like a quarks. Yes. Yeah, that will correspond to flavor. Yes. 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 Exactly. And yeah. So what type of geometric data you're going to extract? Well, the first is the vacuum moduli space. Well, so there is something called Higgs branch, which I write M Higgs. And sometimes I'm going to use notation MQBW, because this is the defining data. So this is known as the Higgs branch. Some manifold, specific manifold of what type? Well, it's called it's a hyperkähler manifold. And the fact that this is hyperkähler corresponds to this thing like n equal 4 supersymmetry, but it's a nice hyperkähler manifold with a triplet complex structures. And then this is indeed a celebrated Quiver variety. So this is nothing but a Quiver variety, which was mentioned a little bit in the previous talk. So this is the famous Quiver variety. Well, if you like, there are other geometries you can associate too, which will not play any role in my talk, but there is also a Coulomb branch, which is also defined by Nakajima and collaborators recently. And so this is also another hyperkähler manifold. And there is a relation between them, which is the famous 3D mirror symmetry. which you can try to relate it to more conventional mirror symmetry. And in fact, if you're mirror symmetry, you might know more in the language of A model versus B model. So if you like, I might call it A model or Higgs model. This is like a B model or Coulomb branch, B or C, yes. B model or Coulomb, sometimes I write. So, and then today I'm going to talk about A/H, A model side of the story. And well, so this is one side of the story, but there is another side of the story, which I'm running out of space, but let me try to write it here. So starting this data, there is another algebraic object, which is the vertex operator algebra. Vertex operator algebra, which is often called BOA. And so I can write it as a vertex operator algebra, of course, defined by the same data, QBW. So this is some infinite dimensional algebra, satisfying some nice actions. And in fact, since you already saw that there are two different geometries, and it turns out you can also associate it a different vertex operator algebra. So this is a twisted vertex operator algebra. If you like, there is also BC twisted vertex operator algebra, which is a mirror of something. Okay, so I don't. Okay, I'm not going to prepare a notation for this, but these are different vertex operator algebra, and there is again a relation between these two. There is a equivalent. There is isomorphic as a vertex operator algebra, which is the algebraic incarnation of this 3D mirror symmetry, which is not completely verified, at least in general, but there are some important works along this direction. So this is so there are two sides of the story: vertex operator algebra side and the Quiver variety side. And of course, we're going to connect the two, in particular this part and this part. And the question is, what is the relation between the two? And that's what I'm going to explain. But the keyword, okay, sorry, I'm running out of space. Yeah, so sorry, I'm a little bit disorganized, but running out of space, but I can write it here. So what is the relation between these two? Okay, maybe it's a good idea to go here. There is some more space here. So you can go both ways. So, well, the operation of starting from here and going there, so this direction is called a chiralization, which is another word in the title. So it's kind of like enriching the geometry and promoting the coordinates into fields of the vertex operator algebra. And that's exactly what I'm going to explain. There is also another direction you can go. If you're given a vertex operator algebra, you can extract some geometry, and that's known as associated variety. So you can go back and forth. Well, of course, this is a little bit of a zero-order statement. If you want to actually prove things, you have to make some caveats to the statement. But roughly speaking, you can chiralize or this direction, and otherwise, it's going back to the variety, which is associated variety. So the purpose of my talk is to explain this in a somewhat mathematical sense. But before coming to the mathematical sense, let me just draw one picture to explain the physics content. So what is the physics content of this? So, okay, so the geometry side I explained a little bit. Given the gauge theory, there is a concept of a vacuum manifold, so-called. There's a moduli space arising from gauge theory. That's you probably have heard of. But what about the vertex operator algebra? It turns out that arises on the boundary of some three-dimensional theory. So in this story, I have a two-dimensional vertex operator algebra, which lives on this boundary. The boundary of some three-dimensional theory. And this is a topological quantum field theory. And it turns out that this is a little bit unconventional, even representation theory-wise. People call it a non-semi-simple. So if you do the representation theory, it's not, well, it doesn't, things are non-semi-simple. It doesn't decompose into simple things. And so there is a little bit unconventional topological quantum field theory, which arises from the so-called topological twist of the three-dimensional 4 theory, which I mentioned. Quiver gauge theory. And the topological twist, there are two different versions, but in my talk, I'm going to talk about the A twist. So I start with the original gauge theory, which is not topological theory. It has gauge coupling constant, dynamics, and everything. And I'm going to do the topological twist to convert into topological quantum field theory. And then the relation between vertex operator algebra and topological quantum field theory is somewhat reminiscent of the classic story discussed by Witten, where there is a Chern-Simons theory in the 3 dimensions, and on the boundary, you have a West-Witten model associated with the current algebra. So this is somewhat similar to that, but a little bit more advanced version, because the topological quantum field theory is more rich. So I won't spend too much time explaining that, but for example, in this topological quantum field theory, there are so-called local operators. Usually in the Chern-Simons theory, there are nodes, but there are no local degrees of freedom, which is gauge invariant. But there are some such local operators here, and there is a little bit more complex structure which arises from this vertex operator algebra. And it turns out that this vertex operator algebra has something to do with the W algebra, for example. Well, actually, affine W algebra, if you want to emphasize, some connection to affine W algebra. And I'm not going to talk about that, but people even define logarithmic VOA by enriching the story, etc. So log and affine W algebra, so connection to this some version of the vertex operator algebra, which I'm going to talk about if I have time. So this is a somewhat broad overview of the context where this arises.
I'm sorry, can I ask a question about
Yes.
3D?
Yes.
TQFT,
Yes.
symmetric, topological quantum field theory?
Yes, it's sorry. Yes, okay. So it is a topological quantum field theory. What is the question?
Symmetric, with 3,
Well, yeah, it's not the same TFT. Well, okay. So in this story, it's not it's not the same TFT per se, but yeah. But I think you can look at I think you can try to look at it that way. Yes, I think. Well, indeed. Although it's a it's let's see. It's a little bit different from that setup. It's closer to original setup where 3D TQFT and then there is a 2D theory in the boundary. Yes.
okay, left is a topological.
Yeah, here it's a holomorphic theory. This is a topological quantum field theory. Yes.
That's a different event.
Yeah, well, let's see. Yeah, I mean, people discuss the same TFT where actually in that context, people discuss 2 boundary conditions. And but here I just have primarily in mind one boundary condition. Yes.
So that you have the right side.
Yes.
You don't have any.
Yeah, but to some aspect, depends what it means. Sometimes some aspect is similar. For example, we're going to discuss some version of anomaly here, color anomaly, and then that's reflected in this 3D TQFT. So in that sense, it's similar. Yes. So yes.
What about the non-inversible symmetric case?
Well, here I'm not going to discuss non-invertible symmetry. Yeah. So in fact, I'm going to discuss in fact, it couples through some conventional symmetry in my situation. So, but in fact, you can try to gauge more unconventional symmetry in the setup, which would be, I mean, it's probably interesting to try to combine that with this more recent developments of non-invertible symmetry here. And in fact, but here I don't think this theory itself has an interest in non-invertible symmetry as far as I know, at least for UN gauge groups. There is an interesting one-form symmetry which you can talk about, for example. But anyway, yes. Okay, other questions? Okay, if not, let me try to explain this correspondence. So first, I actually going to spend a lot of time explaining this correspondence itself. And if I have time, I can mention some theorems which we claim. But let's first talk about ingredients. And then in order to explain the correspondence, I should first describe each of the ingredients, right? So, and then the way I'm going to do that is I'm going to explain this part in such a way that it's completely clear that this is a generalization of this side. And for that purpose, I need to remind you of what is a Quiver variety. So if you already know it, you can think about how to categorize or how to generalize it. But if you don't know, it's a good thing. At least you know something which is considered to be very important in the field. Yeah, so let's go into do the Quiver variety. And the Quiver variety defined by hyperkähler quotient. So it arises from gauge theory. So it arises from some ambient manifold. and there's a group action, and I'm going to go do the quotient, some version of the quotient. Right? So I first have to define the ambient manifold, ambient variety, and then the group action on that. And the ambient variety is actually easy. So I might write that T star left Q EW. So what is this? This is to for each arrow. So in fact, that's where this thing is useful. So here I didn't have any orientations of edges, but what I'm going to do is kind of duplicate arrows in both directions, and I'm going to write down, give a name to this x1, x2, y1, y2, and then here I1, I2, j1, I2, j2, and then this is I3, j3, for example. So this I think is a canonical naming. And then this is labeled by, so okay, so xi, the notation xi is supposed to represent the coordinate associated with this arrow. So you have a collection of xi, yi coordinates, and then alpha i, beta I correspond to I and j. I'm tempted to write small I, but then there's I, so I'm going to write a different notation. So I runs over all the vertices, and then this runs from 1 to, okay, so it's in between the vertices, -1. So there are some coordinates. And then there is an action of the complex equation. So I'm going to do the complex geometry. So I'm going to consider the complex equation, GLB, which is GLBI. You just complexified it. And the action is determined by the moment map, which is given by, so if you look at it, for example, B2, there's a term you can go right and left or left and right, or just come back to this box and go and come back. So you just write everything, and xi minus 1, yi. Okay, maybe there is a minus sign here. So okay, so to make it look better, I might start from yi minus xi minus y, yi minus y, plus, and j and I guess ji. Okay, j is not promoted, replaced by beta I, alpha I, for example. In fact, you have essentially seen essentially the same formula in the definition of the differential of the DG algebra in the previous talk, but in a slightly different notation. But anyway, so this is the moment map, and then you set it to some value, which is a complex number. So this is the value of the moment map, and then I have a quotient, Taylor quotient. So this is so okay. So I need more space. Let's see. Okay, so I don't want to stay here. So, and then the Quiver variety is defined by the quotient of the stable orbits. Mu inverse of 0, stable part, and then do this quotient. So this is the Quiver variety. Sometimes you want to regard this coordinates itself as a part of the geometry, and then I'm going to define the extended variety. M tilde, where this z itself, so these are a set of complex parameters, and which is regarded as a coordinate. So this is like, if you like, a family of Quiver varieties over the space of values of the moment maps, which is regarded as a whole as a manifold. So this is the Quiver variety. Now, so there are 3 ingredients: ambient space, group action, and then the quotient. Now, I want to do the same thing for vertex operator algebra. And I try to imitate what I did before. So the vertex operator algebra. Well, let's see. The analog of the vertex of, well, let's see, Quiver variety is that, first of all, you define the VOA, vertex operator algebra. So that was previously a variety, so I defined the ambient variety. But here I have an ambient vertex operator algebra, which I denoted a V sharp. And this consists of several ingredients, in fact, 3 ingredients. But it turns out that I'm going to write first, only the first one. And you do somewhat very similar things that there. So I have 3 fields. Philip fields which are called the beta gamma ghosts, so-called xi, yi, and let's see. So let's call it the iiji. So the index is the same, 1 to q naught minus 1. So this is 1 to q naught. Okay, so what do you mean by beta gamma ghost? Well, it's better to write down the so-called operator product expansion. So this itself, each of these represents an arrow, right? So and this there is a vector space here, so it's a homomorphism between the two. So these are like a matrices with two indices. And I can write down the indices explicitly. And then yi, ab, and cd, w. And you just write down the natural, let's call the j, and then there's a delta ij, delta ad, delta bc, z minus w. So so now these are fields of the vertex operator algebra, and I'm not going to define formally what the vertex operator algebra is, but instead of a coordinate, it depends on this holomorphic coordinate, which also appeared in the first talk. And then, so these are, you can formally expand with these parameters, and there's a coefficient. So it's like a collection of infinite many fields into one package. And then this means that it's an operator product expansion, so-called, so up to non-singular terms. The singularity is governed by here. And then this is the beta gamma ghost, if you like. Now, you will notice that this structure clearly copies a lot of things which happens here. So this is a natural pairing between the indices. And so there's a coordinate here, z and w, which is holomorphic. That's what I mean by chiralize. So here I have taken some of the coordinates and just chiralize it, meaning that they are promoted to fields of the vertex operator algebra. Well, in fact, I haven't explained the stress tensors. So I should call the vertex algebra. Oh, sorry, maybe I shouldn't delete this. And well, and then of course you want to do the counterpart of the group action, and then that part is also similar. So GL action, the counterpart of the group action. So and then that's the Katsumudi current. For this group action. So here, previously there was a group action, but instead of that, I'm going to say that I can construct some current from these fields. And then that's that you literally almost copy the same formula. xi minus yi minus 1, xi minus 1. Yeah, plus iiji, yes. So this is a Katsumudi current. So this is the one. This is the one replacing the GLP action. And then that spans the Katsumudi current associated with this group's action symmetry. And then actually I'm going to write a little bit more afterwards. And then there's the counterpart of the Taylor quotient or hyperkähler quotient. The counterpart, so the way to imitate hyperkähler quotient, you have to do some quotient in the vertex operator algebra. And in the physics jargon, it's called a BRC reduction. So what is meant by BRC reduction? Well, first of all, you have to add BC, so-called BC ghosts. So these are fermionic or grading 1 also, if it's in Z2 grading, and it satisfies similar relation. It's essentially the same as the beta gamma ghost, but only the statistics is different. And then consider the BRC charge, which is this Z over 2 pi I of Z. And then I'm going to first take this current. So this is a Katsumudi current and Katsumudi. And then there is also a BC ghost current. which is defined. So this BC ghost current. Okay, if I write on the index explicitly in the structure constant, I'm going to write as B and C. So it's actually just the product of B and C. But if you like, I have to be again be a little more careful with the factor. So this is a BC ghost, and so this is like, if you like, a B commutator B and C in the different notation, and then that defines some current, which is the current for this BC ghost. And you just, so this is the Katsumori current for the whole thing, and you're going to define integral, and then define some BRST charge, so-called. And then once you have this BRST charge, okay, I'm running out of space, but once you have the BRST charge, okay, I'm going to use this space again. And then I'm going to define the so-called semi-infinite cohomology. I hope you can see. So this original ambient vertex operator algebra together with the BC ghost. So the BC ghost themselves define some vertex operator algebra, which is denoted by BBC. And I'm going to do take the cohomology with respect to this BRST charge. Well, it's called a semi-infinite cohomology, and that requires some explanation. But if you ever worked on fermions, you might know that there is a Dirac sea, so-called, which fills the energy levels up to the half of the energy levels already filled. It's called the Dirac sea. Yeah, alpha is a joint index, sorry. Yeah, so it's a gauge group, a joint index, yes. So, so if it's SUN, it runs over n squared minus 1 indices, SUN, for example. So that's a joint index. And yeah, so that's the structure. In fact, sorry, I realized that in fact that your question triggered me to write down something, which I forgot to contract the indices. Yes, so I need a C ghost here actually to contract the indices. Yes. So yeah, in fact, this itself is a current. Current itself is BC, but then I multiply by the C, extra C ghost, contract the indices, and then that's the BRST charge. So this is well, this is something kind of cooked up, but it has a classical counterpart, which was apparently studied a lot with classical theory by Constant. But I myself came somewhat from physics viewpoint, at least in this context. So I just learned the
summation Ji or JKM is the summation of Ji.
Yes, that's right. The whole thing. Yes, summation. Yes. Yeah, yes, indeed, the current for the whole thing. Yes. Yeah, so this is the standard BRST charge. It's a little bit cooked up, but it's a kind of the BRST incarnation of taking the quotient procedure. We are doing the gauge theory, so we are more or less restricting the gauge invariant part, and this is just a fancy way of saying it. And the semi-infinite cohomology, as I said, is just a Fermi sea, if you like. So that's a standard way of doing gauge theory. So do enlarge the space, including all the gauge non-invariant sectors, and then project into the gauge invariant part by imposing constraint, which is captured by the cohomology. Now, so far, I should try to go back to here in the Quiver variety, and it seems that so many things are similar. Because yeah, for example, this formula for moment maps is clearly mirrored in this Katsumori current expression. So, which is kind of boring, right? So, in a sense, but it's already exciting. But for example, if you are paying attention to the first talk, you already heard that there is an important difference between quantum case and the classical case in the representation theory, which is that you actually need to specify extra information, which is the level in that context. If you are talking about the representation, quantum affine, etc. And in fact, that's reflected here as well. And in fact, it's related to some geometry of the physics. It's called the anomaly. Well, I called it a quotation mark, but it's actually the standard anomaly in some sense. But I'm not going to explain that too much. But for example, if you have a Katsumori current, right? So, and then you probably might have seen that. So some of the structure, for example, F beta gamma, J gamma, alpha beta gamma, and J Katsumori. So this is the part you expect from the index structure or the group structure. But quite often there is some coefficient associated with the quadratic pole. So, and then this is a parameter, integer known as a level, which, as I said, appeared in the morning talk. And then, so that's the important difference, in fact. So if you do, this is the quantum effect in a sense. If you like, you can put in the H bar here. So if you want to do the BRC reduction in the quantum sense, you have to, the new contribution. And in fact, it turns out that you just follow this procedure literally. This Q is not nilpotent. If you just literally follow this. So in fact, I mentioned the anomaly, but you don't actually need to know anything about anomaly or anything. You just follow the procedure, compute the Q squared is not 0. So you cannot define the cohomology. So that's the interesting story. Of course, if it's not Q squared is 0, you cannot define the cohomology, so you have to change the setup a little bit. In physics jargon, it means that if here's anomaly, you have to cancel the anomaly to make the theory consistent. And then there's not the unique way to cancel the anomaly. Actually, there are millions or actually infinitely many different ways of canceling the anomaly. So, and then depending on how you cancel the anomaly, you get a different vertex operator algebra. But I'm going to present a somewhat minimalistic way of canceling the anomaly. And then, so that is to, so that is to just add the matters somewhat by hand. And then that's what I'm going to do. So, and that's why I left out the space. So I'm going to add free fermions by I psi I for each vertex. Well, you might have heard that the fermions have an anomaly, chiral anomaly, associated T index theorem, etc. So I'm going to add the fermions to generate the anomaly. And in fact, this is enough to cancel the SU part of the U anomaly. So this action of GL, and then, well, traceless part is canceled by this, but you need extra matter to cancel the U1 part of the anomaly. And then for this, I'm going to introduce a so-called Heisenberg BOA, which is defined by this condition that HIZW has the form like a Cij Z minus W, where C is the Cartan matrix. So I extruded something extra. In the quantum field theory language, it means to add the degrees of freedom localized on the 2D boundary. But here, in this BOA language, you literally add by hand some of the fields. And then you also have to modify this equation. Well, in fact, this is like a fermion. So in a sense, adding the fermion has the effect of, so for each vertex you add the fermions, and it turns out this is converted into super framing. W1/W2, D1, this is the. And of course, I didn't specify how many fermions. And it turns out that this number is given by Di is equal to Wi plus Bi minus 1 plus Bi plus 1 minus 2Bi. So this is the number. And of course, this should be non-negative. So I'm going to assume that this is non-negative for all the vertex. So, so this is the Di copies. So I'm going to add the Di copies of fermions. It's like, yes, changing the framing. Yes?
Do you have this anomaly even in the superconformal case?
Well, let's see. In the superconformal case, you don't actually need it. In the superconformal case, this is actually exactly 0. And that's a vanishing the beta function, which is exactly the same condition as this. And in fact, that's actually very important because probably many of you might have heard about this type of topic in connection with 4D n equal 2 SCFTs. Not in the context of 3D n equal 4 I'm talking about. And in that context, people assume superconformality from the outset, as in the original aspirator paper. So this was also 0. So you don't need to include any of these things, in fact. But you actually still need to incorporate in our discussion Heisenberg part, but at least for this thing, it's not necessary.
About the six-dimensional superconductor, three correspondence.
Well, it's a very different from the 3D correspondence, and but it's somewhat similar in spirit that well here, yeah. So at least the original version of Lasteri et al. Is that you're going to start with 6 dimensions, and then compactify it on a 2 manifold to get a four-dimensional SCFT, and inside the 4 dimensions you're going to get the 2-dimensional plane. That's where the vertex of this operator algebra lives. Now, here, I'm going to have, I'm starting with, my setup is, well, essentially related by dimensional reduction in some cases, but in general not. I'm starting with the 3D theory. And yeah, so if you like, you can try to realize realize them from string theory. But the context itself is actually very different, yeah. Well, I myself have worked on a lot about 3D, so I'm happy to talk about that maybe after during the break or so. But yeah, but its context is very different from that. It is somewhat similar to this so-called 4D2D of the last et al. But the important difference, in fact, many of the statements about the connection to Quiver variety is more manifest in this 3D setup I'm talking about. Any other questions? Yes.
So can you actually realize this in terms of particular boundary conditions? Like why this?
Well, let's see. Yeah, I mean, it's actually not well. If you want like a more physical boundary condition, by including extra matter, etc., typically it's not like we have a proof, but typically you get the theory with a larger central charge. You need a little bit more matter, for example. Here, I just added the Heisenberg by hand, but in a typical, so in fact, in our paper is a little bit confusing because this minimum we call it maybe B, and then the more physical one we wrote the boundary BOA with the thing, and these two are distinguished in the paper. But yeah, but these are like 2 different versions of anomaly cancellation, and as I said, this is only 2 examples of there are many different ways of cancelling anomaly.
You mean the different cancellations for your?
Yeah, so there are different anomaly cancellations giving rise to different vertex operator algebras. Yeah, so everything depends on the choice. And I'm talking about the specific one, which is kind of minimal. Yes. It's not completely clear what I mean by minimal, but in a common sense, it's a minimal choice for canceling the anomaly. But partly because if there's a U anomaly, like you have to cancel it. So there's actually a cancellation from other things, but has a minus sign, and I just literally add something to cancel it. Yes. And Heisenberg, but I should emphasize that it looks like this is like very artificial, but at least you have already seen something similar here. That's this parameter z. So the value of the moment map, that was just a number, and I just included in the definition of the extended Quiver variety. But this parameter z is actually promoted to the fields of the Heisenberg. So this we didn't see because that was not needed, but this Heisenberg is the counterpart of this image of the moment map. So in fact, everything is kind of promoted to fields of the vertex operator algebra.
I'm sorry, what kind of mirror? The control mirror or the chiral mirror?
No, it's yeah. For example, it even grows a superconformal case, for example, as a special case when d was 0, for example. So yeah, so it's a very different from that. Well, it depends on the situation, but yes. But I mean, but actually, interesting. The infinite dynamics itself contains a lot of interesting things. Sometimes there's RG flow, and then some of the operators, like a monopole operator, they decouple, and then that's related to that's a geometric counterpart in Quiver variety, etc. So there is an interesting RG effect in general. You can discuss the superconformal case where there's RG is trivial, but you can also discuss the RG flow itself. Although in the original theory, although in this setup, I'm talking about the twisted theory, where I already converted to the twisted theory where the RG effect is trivial. So, at least the Baruch dynamics is relatively trivial in that sense, apart from the topological data because it's a topological quantum field theory. Okay, so that's the So and then yeah. So in fact, well, okay. Then I'm not going to write down everything, but yeah. For example, so I have to add 5 psi, etc. Because now I have these fields. So these are very similar laws, 5 psi, and then if I do this, I said previously 0, but now it becomes 0 after all these manipulations. So that's how you define the vertex operator algebra. And yeah, so that gives the A definition of a vertex operator algebra, which I denote by V. So that was the original one, which was which I used in the introductory part, VQBW. Now, it seems that I have like a 15 minutes or so. So then I can give you maybe 2 theorems or so regarding this vertex operator. It gives a definition of the algebra. And of course, the question is, the definition itself is inspired by Quiver variety. But of course, it doesn't guarantee that the actual thing has anything to do directly with you need to find a concrete statement to relate it to the Quiver variety, right? So, and it's actually not that easy, partly because this is defined as a cohomology. I mean, everything is explicit. You can be explicit with everything. But of course, it's a cohomology problem. First of all, you have to pick up some operators which is compatible, which is in the cohomology, if you like, cued by this BRHC charge. And finding that is not the most difficult part. You can take some combination and zero, etc. But of course, it might be in the image of something, right? So it might look like there's some operator, but it might secretly be zero inside the cohomology. Of course, that's always the case. And so you need to find a good way to compute it. Of course, some standard techniques like a spectral sequence of help, but it's a reasonably non-trivial question. So now, but nevertheless, there are some statements you can make. So, well, for example, an example, let's see. Okay, so for example, one example, so is this Quiver. Yeah, I hope I'm not making a mistake. Yes. So let's consider this Quiver. In fact, in this example, the D is 0. It's a supercomponent, if you like, if you just compute it. And so let's this Quiver. Relatively simple Quiver, 3 node. And this is, I didn't draw anything, but you can think of it as 0. Framing dimension is 0. Okay? And then you can define some vertex operator algebra, D, VW. And then, as I said, it's not easy to find all the generators, etc. But you can it's not that difficult to find some generators. For example, here I have the x and y's, right? So x1, y1, and I1, I2, j1, I2, j2. And then you can find some nice generators. For example, you can find, so this is the vertex 1, vertex 2. So you can start with vertex 1 and go to vertex 2. So for example, in this case, I1, Y1 to go here, and then there, J2. So yeah, so maybe I took this route. And J1, 2 is, I take this route again, this time. So like I2, X1, J1, for example. So these are nice things that you can check after these are gauge and BRC invariant. And then there is also G11. So these are like matrices, I1, J1, which is like going back and forth between here, and it has indices. So these are matrices. So this is an index. It turns out this is not BRC invariant, but you need to correction by Heisenberg. Well, sorry, I forgot the precise formula. But yeah, I think if you write on the index ij, this is delta ij, and then this should be h1, the h1 associated with this vertex. Maybe something like that. So you need to correct it by Heisenberg, which is reasonably non-trivial, but you can check. And then you find 3 generators. And it turns out that then you can compute this OPE. So these are all Q exact. Not the Q cross, sorry. So element of the cohomology. And it turns out these are the generators, in fact, so-called strong generators of the W algebra. -4 and GL3. Sorry, the other way around. So GL4, yes. GL4 and -3. And then so-called minimal nilpotent orbit. And then there is it turns out you can check that this is part of the vertex operator algebra. So this is a homomorphism of the vertex operator algebra. And so this is, I'm not defining it what this W algebra is, but given a real algebra together with a nilpotent element and the choice of the level, there is a W algebra, and then there is a homomorphism from here to there. I should say that this is not a critical level because the critical levels were mentioned in the morning. It's not a critical level. If you shift by dual Coxeter number, this is 1, whose inverse is also 1. So in fact, this is the point where it's self-dual under the Faking-Fuchs duality. But previously, in the previous talk, it was like a relation between 0 and infinity. 0 and infinity are inverse to each other. But here it's 1, so it's a self-dual point of the Faking-Fuchs duality, for whatever the reason. So there is nice relation of this W algebra to this thing. So in fact, but this itself is not the W algebra. So this is, of course, you have to prove it, but we believe that this is not isomorphism as a vertex. So this is larger. There are more generators. There are fermions and everything. So this is definitely larger. So it's some interesting algebra, which naturally comes from Quiver varieties. And it contains the W algebra. If this is really embedding, yes, which also requires a proof.
Let us GL4 come.
Sorry, what?
GL4.
Yeah, GL4. Yeah, in fact, that's a good question. In fact, that's something I didn't explain. So in fact, this is the, so in fact, this is associated with the, so in fact, the Higgs branch. So you can ask, before coming to the BOA, it's not, maybe we should start with the geometry. And you can ask, what is the Higgs branch of this theory? And it turns out that this is the nilpotent orbit of GL4 associated with some nilpotent element, 211, I think. So this is some partitions. Yes, well, in fact, well, standard notation with transpose of this, etc. But anyway, so it's a set of matrices with a specific Jordan form Flock, 4 by 4. And so that GL4 is related with this GL4. And in fact, that's one explanation. Well, there's a more physical explanation. This is like a 3-dimensional theory. It turns out you can regard as the boundary of a 4-dimensional theory, which is the GL4. So that 4-dimensional theory is 4 equal 4 super mills, which after twist becomes the Kapperstain-Witten theory, relevant for geometric Lagrange. So it's not completely unrelated to the previous talk because the Kapperstain-Witten theory is exactly the setup for geometric Lagrange and the connection of the conformal field theory to the Gordon model. So so that's an example. And in fact, if you change some theory, I'm not going to write it down, but if you like, there is also, you can find a theory of this version, GL minus n minus 1, for example. But if you make the quiver larger and larger, I can keep doing this, but it turns out that this type of manipulation becomes horribly complicated, in fact. I didn't write down the OPE between these, but it's actually very, very complicated. And even if you find it, it's not easy to compare with the existing one. So you need to check if it matches the generator relations of the W algebra. In fact, but people are still writing. This is defined by the BRC reduction, but for the W algebra, finding explicit generators and relations is already some work. So you have to go through a lot of heavy lifting to discuss that. Well, let's see. So at some point, you begin to wonder if there should be a more systematic procedure discussing this vertex operator algebra. And then that's what I'm coming to next in the remaining 8 minutes. And that's related to the free field realizations. Well, I don't have enough time to explain everything, but let me try to give you a basic idea. Again, my consideration motivated by geometry, and then try to uplift to the vertex operator algebra. So you can ask, what is the way to simplify the geometry? And that is the localization, connecting local to geometry. So what I mean by that is the following. So I have a Quiver variety, which people kind of know the dimension, property, have a Kera, etc. But it's still a complicated variety. So it's still a variety, right? So but if it's a complicated variety, what you should do? Well, whatever the variety, you go to a local patch, it becomes simpler. So the nice way is to consider the open set in the algebraic sense. So this is the Zaleski open set, where some f is non-zero. For f is some polynomial. Well, but the polynomial in what? So these are the coordinates. So this itself has fields like xi, yi, ji. So for example, some of the i's are non-zero. you go to that region, right? So, oh, maybe I was mentioning, I used the notation alpha I before, sorry, I'm mixing up. And then, so if you go to the region where some of the i's are non-zero, and you go to a smaller patch where things simplify. And in fact, does the formula remain? Yeah, in fact, fortunately, the formula remains. So for example, the simplification is that if alpha is non-zero, for example, you can use this formula to solve for beta I equals something, for example. So there is a constraint, but you can actually solve for the constraint and eliminate some variables. So it's an elimination. Of course, when you're doing that, you assume that alpha is non-zero, so it's not the same geometry, but you go restricted to some particular patch where you can invert it. And then you can try to ask if there's any counterpart of this procedure. Well, if you go to the smaller patch, so this is like a standard relation between the ideals and then the sets in algebraic geometry. So let's see. So if you go to a smaller region, then you're going to have a larger vertex operator algebra. B prime, for example. So I might write as a BF or something, which is a little bit simpler because the starting geometry is simpler. And then if you keep doing that, you end up something very, very simple. And something that very, very simple means that in this context, it's a free vertex operator algebra. Free field vertex operator algebra. Sorry. Yeah, a fine chart. Yeah. So yeah, that's right. So the chart, yes, and yeah, and yeah, and then so what in this setup, if you keep doing that, geometry becomes so trivial that the counterpart of that is that you get the free field BOA. And now that means that if you keeping track of what happens here, then you have an embedding into the free field vertex operator algebra. And this is known as a free field realization. Okay, maybe I shouldn't use this color because people cannot see free field realization. So that's the main idea. But of course, if you want to turn this into mathematics, some procedures are necessary. And that's where the previous works of Arakawa and, for example, Marikov and others, and Kuwabara and others turned to be useful. So in fact, if you want to formalize it, you need to consider, yeah, so I have only 3 minutes. So let me say, so need to formalize. So in practice, need to formalize, need to define sheaf of vertex operator algebra. So it depends on QB, and then it in fact defines H bar. In fact, you need to keep track of H bar, so you need to talk about H bar algebraic vertex operator algebra. But because here it's an interrelation relation, right? So you need to defines the sheaf. So and then take a global section. And then set H bar to 1. So that defines some BOA.
Sheaf over the Quiver variety?
Yes, so sheaf over the Quiver variety, yes. Yes. So so here I explained these things, but I'm going to formulate the whole thing, yes. Whole thing. And then of course, eventually I want to go back to the original thing, right? So that's what I mean by global section, yes. So, well, of course, each part, it's like each part is a free field BOA, but then they kind of grew together. Just like varieties obtained by starting with a trivial geometry and then grew them together. And I'm going to take a global section, and that defines the BOA. Well, of course, this itself is a priori different from the original BOA we started with. And yeah, so I'm afraid I don't have time to write down the proper theorem. For that, I refer you to. So under some assumptions, which is spelled out in a paper, it just takes extra 4 minutes to write it down, so I'm not going to write down the assumptions. And then under some assumptions, there is embedding. Of the vertex operator algebra. So this is the H bar. Sorry, I deleted H bar, so I don't need the H bar. Under some assumptions mean that, for example, when Q is linking, like A and linking, for example, when the quiver is simple case, then this is an injection. So this is an injection. Well, embedding, yes.
So embedding what?
Yeah, embedding this into here, yes.
In the parameters.
Yeah, so to this, embedding this vertex operator algebra into here, yes.
The complexity H bar.
Well, no, H bar is actually, yeah, so I said, going to send H bar to 1. Here there was a H bar, but then I set H bar to 1, so this one itself doesn't have any H bar.
Okay. Left you have the view A and then embedding on.
Yeah, so this is a, yeah, so Vertex is a vertex algebra. In fact, there's a vertex super algebra, yes.
Okay, I see.
So, and in fact, that it contains the embedding, that stress energy tensor is also compatible with this embedding, for example. And then, well, first of all, that's a homomorphism, but then there is no kernel, essentially. So that's a statement. And then in fact, that's mapped, then that's, what I was saying before is that this itself has a free field realization, which I'm not going to write. And then the second theorem is that, so there is this BRC reduction. So, which define this BOA. In fact, in general, it might have non-zero elements in this gradient. This P is not a ghost number. In general, this is not, there is no guarantee that this is zero, even apart from the zero component of the cohomology. It's a cohomology, so it's graded by something. But it turns out that this is zero if P is smaller than negative part.
This nilpotent sense can construct.
Well, let's see, so nilpotent charge is there, so you can define the cohomology. But there could be ghost number non-zero part contributing it. So in the old-fashioned string theory, people talk about, for example, no-ghost theorem, and it's that type of theorem. And here we didn't prove the whole thing, but at least in the negative part, this is zero. So there is some vanishing result under some conditions. So so this is what the final part is a little bit technical, but at least the point is that I explained the similarities parallel between the geometry of the Quiver varieties and Vertex operator. Later I tried to copy, but with important differences, like quantum corrections. And that gives, first of all, some specific vertex operator algebra. And that raises a lot of questions. What is it, for example? What does it contain? What is the connection to, for example, even, I didn't discuss the listing, but your quantum group, for example, so-called small quantum group. And also, like, for example, what is the free field realization? All sorts of questions. And not everything is proven, but we now have a systematic procedure to begin addressing that question. Sorry?
What is B-sharp?
Yeah, so B-sharp is the ambient one, so before taking the BRST quotient. So this is the one before taking the quotient, which I defined before, written in terms of the xi, yi, and psi f, phi I, and then the Heisenberg. So without any group action a priori. So that was what I denoted as B-sharp. So that's like, without group action, everything is free, and it's effectively. And then only afterwards do the BRST reduction. And so that was the definition of the semi-infinite cohomology. And so that was the definition here. But of course, typically in the definition of the vertex operator algebra, you take a zero component of the cohomology, but you might worry about the other components, which in some cases show that it's vanishing. So yeah, so okay. So maybe that was a little bit technical, but that's the main point. And in that way, you can connect the geometric part and the algebraic part. But there's a lot of questions. And in fact, the vertex operator algebra themselves are complicated, but the geometry provides a useful guideline as to how to think about the problem. Thank you.
How would invisible two?
Yeah, Fermi C. If you are, I don't know what your background, but if you are a physicist, you might call it a Fermi C. Yeah, Fermi C. Yes. So, but if you don't like it, so you define Yeah, so you need to choose a reference, so-called vacuum, so-called in this vertex operator algebra. And you let half of the modes act on zero, trivially. But then, so it's somewhat similar to like PBW decomposition and things like that. So creation operator, annihilation operator, sorry, there are many different words of saying the same thing. So yeah, so you need to fix the structure, and that's the semi-infinite cohomology. So yeah, but it's some version of the cohomology with respect to some fixed choice of vacuum, yes.
Okay. Can I ask you this?
Yes.
You have okay, discussed about the three-dimensional case. How about the start with four-dimensional and do
Well,
can you make some comment?
yeah. In fact, the relation between 3 dimensions and 4 dimensions is somewhat subtle. Like for example, in 3 dimensions, it's for example, there is anomaly, which is a 2D theory. But anomaly or not, it highly depends on the dimension. Like partly because one way to say mathematically is that there is a C1 first-order class in 2D, for example, but in 3 dimensions, it's 0. So there is a discrete anomaly, but things are anyway. So the topologies are very different in even dimensions, odd dimensions. So some of the discussions here go away. In fact, and also some of the limits that people typically start with the superconformal case only when the integer di I was writing with 0. But also, people in 4 dimensions sometimes define the quotient with just the SU, not for U, for example. And in fact, so there's a lot of discussion on the 4D theory, 4D vertex operator arising from 4D. And yeah, there are some important differences, in fact. And but there are also a lot of differences. For example, if you talk about 3D mirror symmetry, people call it 3D mirror symmetry because the 3D is important. Partly because if you go, well, you might think that you go to 4 dimensions on S1 with a finite radius. But then, for example, Higgs branch and Coulomb branch is a very different geometries, actually. The 4-dimensional Higgs branch is the same, but the 4-dimensional Coulomb branch is actually like a fibration over the base manifold, which is a cyber-Witten geometry. So, and then the size of the fiber shrinks. So it's there are important difference between, in that sense. Although, but there could be a lot of generalization because, for example, we heard about the Q W algebra. For example, you can ask what is the counterpart of that, and then there's some tentative answer, which takes a little bit of time to explain that. But at least eventually, this one originates from the so-called 4D unequal 4 theory, and you can go to 5-dimensional theory with a finite S1 that introduces the extra quantum parameter. And in fact, that's the context where people discuss the so-called Q-Lagrange correspondence. With the 5D gauge theory as one, with the 4D unequal 4 theory, whose boundary is a 3D theory, whose boundary is a BOA I'm talking about. Sorry, maybe too fast. But you can uplift to 1 dimension higher more or less, and then you can introduce, at least in principle, the Q Lagrange and the Q W algebra, for example. So there are a lot of ways to deforming the theory.
Okay, can I let's start also 6-dimensional superconformal field theory,
yes.
and complete Y 2 dimensions, and then left of the 4 dimensions. And then now just before say something about the can you apply the same things as these kind of things? Start with the
well, let's see. Sorry, without context, let's see. So yeah, I mean,
understand the 6-dimensional superconformal field theory on the basis of this kind
okay.
of things.
Yeah, well, let's see. Yeah, I mean, well, that depends on the setup. For example, so for example, one setup is you can start in a 6-dimensional theory, compactify the 2-dimensional manifold, for example. You can have a 6-dimensional theory on a Riemann surface, and you get the 4-dimensional theory, and then further on S1, and you get the 3-dimensional theory, for example. Yeah. And in fact, it's known that some of the 3D theories arises this way. It's actually interesting. It's not the linear quiver I have. But typically, I have trivalent vertex. So some people call it a Sicilian theory. For example, for example, if you have something like this, it looks like a Quiver thinking for E6, I guess. And in fact, this is a theory discussed as a mirror of the so-called dimensional. So sometimes this is a non-Lagrangian theory, Algebras theory associated with the irregular singularity. So here, sorry, maybe I took it too much, but here I can have a Hitchin system with the irregular singularity, and you have a 4-dimensional non-Lagrangian theory, Algebras theory. You can compactify it and then take a mirror, and then you got this Sicilian theory, for example. And then you can discuss the BOA associated with this too. Of course, the Quiver structure is a little bit different. So some of what I said doesn't literally. Some of the theorems, the setup apply, but some of the theorems I said doesn't apply. But in principle, you can study these things. And that case is more interesting because it's actually the middle of the series, not the Lagrangian theory. So you need to discuss the boundary BOA associated with the non-Lagrangian 3D theory, which is more tricky. You can simply work things out explicitly. And so there are a lot of questions of that type which you can discuss.
questions?
Yeah. So first, you mentioned that in the example minimal operator on chair 4,
Yes.
physical level -3 because maybe some kind of self-theory. Right?
Well, yeah, it turns out, I don't know the deep reason for that, yes. But it turns out that if you work that out, that's the number. And I don't know the number reason. I mean, yeah. Yeah, for example, one way, yeah, I don't know that, yeah, so in fact, one answer which is not unrelated to the answer which appeared in the morning talk is that, so for example, there is this, I was talking about the localization and embedding the free field, and then you can talk about the standard double algebra associated, yeah, and then minimal nilpotent orbit, for example, and then this is the standard Wakimoto realization in that case. It turns out you can work everything out explicitly. It coincides with the Wakimoto realization. And in that case, if you do with the GLN, you have to do this process roughly like n times, n minus 1 and 2. And each time the level changes one by one. So there is a shift of level, which is somewhat reminiscent of the comment appeared in the morning. But I don't know the deepest reason why that particular level.
Another question is that with this Quiver variety, you can, for example, obtain some consumer algebra.
Yes. Yes, yes, yes.
I wonder whether we can some kind of do this for like this kind of chiralization or whatever.
Yeah, I mean, in fact, yeah, that's right. So it's an interesting story. Like, for example, there is this Y algebra story, and then how to merge together with this. And yeah, so that requires some, yeah, I mean, like gathering of all sorts of thought. But here, for example, if you start with the, so Y algebra arises from 4D equal 4 on the region. For example, if Y algebra starts with 4D equal 4, 3 regions, and then here you have a 2D BOA. And here, here it's like a boundary. Here, what I said is that there is a 2D BOA on the boundary of 3D theory, right? So that's what I said. But there is actually a useful way to look at this from the somewhat four-dimensional perspective, which is related to some of the, well, at least in some cases, not exactly the case I'm talking about, but that you can try to realize this by the wedge of 4D theory, 4D n equal 4 theory, and then such that there is a 2D BOA here. And if you shrink the wedge, you get the three-dimensional theory, right? So so it's a limit of tau goes to, well, you have tau of S dual pair, but in some duality frame, tau goes to I infinity or something of that limit. So it turns out that there is actually, before the BOA, there is actually a parameterized version of the BOA, which sits at the corner, for example. And then this picture looks very close to here. So in practice, well, let's see, I shouldn't say in practice. In principle, you can do a lot of stuff. You can have a wedge of something complicated, and then with each of the n equal 4 in region, and there you have a junction of something, and then even like a loop or something like this, all sorts of crazy stuff sometimes, and then you can shrink. So this gives 2D BOA at here and there, but if you want to connect the 3D picture, you can kind of shrink, for example. So, and that gives a zoo of BOAs, which is yet to be discovered, where almost none of that has been discovered ever. And then certainly that has a lot to do. Some algebraic structure associated with that is, goes beyond most of the conventional algebras, even the quantum toroidal, etc. But some of the more general ones, it has something to do with Quiver Yang Quiver quantum toroidal algebra, which I worked on. But, so I think there's a lot of that to be discovered. And also I should mention that in fact, one of the particular motivation for thinking about this is not this context, but if you do a little bit so-called Chern-Simons gazing, you can enrich this vertex operator algebra to something logarithmic vertex operator algebra, so-called Fagin-Tupunin vertex operator algebra. And then this construction arises in that particular context, which is non-logarithmic. So it's actually, yeah, it's not the rational CFT, but it has some still nice properties. People call it quasi-lease. But in any case, so even from the purely vertex operator algebra side, there are some basic ones. And then, but the point is that even those fancy stuff should be considered a very, very small example of the whole construction. So because of that, I think that's very exciting. Yes.
This is my question, but is that vertex algebra directly related to arc space
Oh yeah, it has a lot to do with the arc space. So in fact, this vertex operator algebra itself is well, it's of course the vertex operator, not a space. But for example, when you try to connect it to so-called associated variety, which I didn't have time to explain, you need to go to the to the geometry, right? So not the vertex operator algebra. And then that's an operation of taking an associated variety. But now, if you have an associated variety, you can try to go backwards to some extent to this vertex operator algebra. And it turns out you cannot completely go backwards, but more or less, yes. And that's where the concept of arc space appears. And in the conformal field theory language, going to the arc space means that you're going to consider the arc space. Yes, arc is in the arc space. And in conformal field theory language, that is to consider descendants. So typically you have the modes like an, but you can take the A0 part or the lowest part, like and then namely you set the derivative to 0, for example. But once you know that, you can try to generate the whole thing by so by kind of enlarging this to here, and that is a BOA counterpart of the going to the arc space. Yeah, so the arc space involves the map from S1 to something, and right. So in that S1 action, S1 means that you can expand with this Fourier mode. That Fourier mode is this thing. So it's very relevant indeed.
Okay, now let's start.
Thank you.